Welcome, data aviators, to a high-flying adventure in our machine learning journey. I'm thrilled to be here with you, and today we're diving into a regression task using a powerful, interpretable model from the Interpret library. I'm running this in Google Colab, breaking it down into clear code blocks so you can follow along as we explore a dataset about airline passengers. Let's get our engines started by setting up our environment and gathering our tools. I kick things off by installing the Interpret library in Colab with pip3 install interpret. This library is our ticket to explainable AI, giving us clear insights into our model's decisions. Next, I import the essentials: NumPy for numerical operations, pandas for data manipulation, and Seaborn to load our dataset. From Sklearn, I bring in train test split to split our data, and mean squared error and our toScore to evaluate our model's performance. From Interpret, I import explainable boosting regressor from the Glassbox module, our star model for today, along with the show function to display explanations. I also set up inline visualizations with setVisualizeProvider and inlineProvider, ensuring our plots render directly in Colab. With our toolkit ready, let's load the data and take off. I load the dataset using Seaborn's loadDataset function to grab the flight's dataset, and I call dropna to remove any missing values. Though this dataset is clean, so we keep all 144 rows. I print df.head to take a look. Year 1949, month Jan, passengers 112. The next row shows year 1949, month February, passengers 118, followed by March with 132 passengers. This dataset captures monthly airline passenger numbers from 1949 to 1960, with 144 records, 12 months per year for 12 years. Each row includes the year, month as a string, and passengers, the number of passengers in thousands. It's a time series dataset often used to study trends in air travel and will predict passenger numbers based on year and month. Let's pre-process the data for modeling. Since the month column is categorical, strings like Jan, February, I convert it to numerical values using PD factorize, which maps each month to a number. Jan becomes 0, February 1st, March 2nd, and so on up to dec as 11. I overwrite the month column with these values, so our head now has year 1949, month 0, passengers 112, and month 1, passengers 118. I define X as the features year and month. These will help us predict passenger trends over time. For Y, I set the target variable as passengers, the number we're predicting. I split the data using train test split, allocating 20% for testing and 80% for training, with random state 42. This gives us 115 training samples and 29 test samples, ready for our model to take flight. Now, I introduce our model, the Explainable Boosting Regressor, or EBR, from Interpret's Glassbox module. EBM, the Explainable Boosting Machine, is a machine learning framework that combines the power of boosting, iteratively improving weak learners, with interpretability. Unlike traditional boosting models like XGBoost, EBM uses a technique called Generalized Additive Models plus Interactions, GMs, fitting simple functions for each feature and their interactions, making it highly transparent. EBR is the regression version of EBM, designed to predict continuous values like passenger numbers, while offering clear explanations for each prediction. I initialize the EBR with Explainable Boosting Regressor, call fit on xtrain and ytrain to train it, and let learn how year and month influence passenger counts. Once trained, I make predictions on xtest with predict, storing them in ypred, and evaluate with mean squared error and R-squared score. The results are impressive. Mean squared error 54.021. Root that, about 7.35 passengers off per prediction. R-squared score is 0.9946 to 99.46% of the variance explained. For passenger counts ranging from 112 to 622, this is a fantastic fit. Next, I dive into the local explanation to understand the model's prediction for a specific test sample. I call eb_regressor.explainLocal on the first test sample, xtest slice 0 to 1 and ytest slice 0 to 1, and extract the explanation data for this record with local explanation to data 0. I print the details. Predicted value 355.258. True label 359. Very close. Only 3.74 passengers off. Feature contributions show year at 102.939. A strong positive push, meaning the year significantly increases the predicted passenger count. Month contributes minus 12.994, pulling the prediction down, and the interaction term year in month adds minus 19.130, further adjusting downward. On screen, you're seeing the local explanation plot, a bar chart for this prediction. The year bar stretches far to the right in orange, showing its dominant positive contribution of 102.939, driving the prediction up. The month bar, in blue, juts left at minus 12.994, and the year in month interaction, also in blue, extends left at minus 19.130, tempering the prediction. The final predicted value, 355.258, is marked at the top, just shy of the true 359, a clear breakdown of how year and month shape this prediction. I move on to the global explanation to see what drives the model's decisions across the entire dataset. I call EBR_regressor.explainGlobal, extract the global feature importance data with global explanation.data, and print the values. Year has an importance of 99.223. The most influential feature. Month has 31.448, and the interaction year in month has 15.629. I display the plot with show, and on screen, you're seeing a feature importance graph. The year bar towers at 99.223 in blue, stretching far right, showing its overwhelming role in predicting passenger numbers. Air travel grew significantly from 1949 to 1960. The month bar, at 31.448, also in blue, is shorter but still significant, capturing seasonal trends. Think summer peaks versus winter dips. The year and month interaction, at 15.629, is the smallest blue bar, indicating that while interactions matter, they're less impactful than the individual features. This plot confirms that year is the primary driver, with month adding seasonal nuance and their interaction fine-tuning the predictions. Let's reflect on these outputs. They're a flight plan for understanding air travel trends. The head showed 1949, month 0, Jan, passengers 112, rising to 132 by month 2 Mar. Early signs of growth. After factorizing, month 0 to 11 makes our features numeric, ready for modeling. The mean squared error of 54.021 means predictions are off by about 7.35 passengers. Excellent for counts spanning 112 to 622. The R-squared score of 0.9946 confirms the model captures 99.46% of the variance, a near-perfect fit. The local explanation for the first test sample predicted 355.258 against a true 359, with year contributing 102.939 positively in orange. Likely a later year like 1958 boosting passenger numbers, while month at minus 12.994 and year and month at minus 19.130, both in blue. Adjust for seasonal effects, perhaps a quieter month. Globally, year's importance of 99.223 underscores the growth of air travel over the years. Months 31.448 captures seasonal patterns, and year and months 15.629 shows how specific year-month combos, like summer and later years, refine predictions. EBR's transparency lets us see exactly how these features shape passenger forecasts. To land this journey, we've soared through the flight's dataset, a 144-month record of air travel from 1949 to 1960, and train an explainable boosting regressor, achieving an R-squared of 0.9946 and mean squared error of 54.021. The local explanation showed year, driving a prediction of 355.258, adjusted by month and their interaction, while the global view confirmed year's dominance at 99.223, with month and interactions adding nuance. EBM's interpretable approach, breaking predictions into additive feature contributions, makes EBR a powerful tool for regression, balancing accuracy and transparency. Grab this code, experiment with more features, and chart your own flight path. I'm exhilarated by this air travel analysis. Hope it's got you ready for takeoff on your next data adventure. See you in the skies.